Welcome back. Today we're going to be talking about probability concepts. Our content objective is students will be able to find the approximate likelihood that an event is going to happen. Language objective is students will be able to describe the likelihood of an event's outcome. Why am I learning this? Well, it's important for real-world problems like determining if you should participate in an outdoor event if there is a 75% chance of rain. So first, let's take a look at this. We have a bag that consists of 5 white marbles. If you were to reach into that bag, what color do you think you will pick? Let's face it, they're all white, so you know you're going to pick a white one. So that is what we call a certain event. Certain. For sure, you're going to pick a white marble. Now, if you reach into the bag, what are the chances you're going to pick a blue marble? Hopefully you're going to say there's no chance at all because there are no blue marbles in that bag. This is what we refer to as an impossible event. There is no way you can pick a blue marble out of that bag since all there is are white marbles. Okay, let me ask you some more questions. If you reach in the bag once, are you more likely to choose a red or a blue marble? Hopefully taking a look at that, you can see right away it's more likely for you to grab a red marble than you are to choose a blue marble. But why? Well, because there are 3 red marbles and only 2 blue marbles. So now let me ask you yet another question. What would I have to add to the bag to make it equally likely between grabbing a red or a blue? Hopefully you said that you would have to add a blue marble. Okay, why? Because that way there's equally 3 red marbles as well as 3 blue marbles. Now, if I change the instructions and said, what else could you do? Not necessarily putting marbles. What if you took away marbles? Then you could have also taken away a red marble. Oops, I went by too fast. You could have easily taken a red marble away, making it 2 red marbles and 2 blue marbles. So probability is usually expressed as a fraction, or sometimes a decimal, between 0 and 1. Okay? So 0 being it's impossible, and 1 being certain. Other times, probability is expressed as a percent between 0 and 100%. So again, 0 is impossible, and 100% being it is certain. So here we have a scale. We have impossible, unlikely, equally likely to occur or not occur, likely, and certain. Using this scale, I'm going to ask you a couple questions. Okay, you're going to try to figure out where does it belong on this scale. And I apologize, the word "the" got cut off here. It says here, number 1, you will see a live dinosaur on your way home from school today. If you're serious, you know your answer is impossible. Okay, because dinosaurs are extinct. Number 2, what are the chances that you have school today? Well, guess what? In class, you are currently here today, so we're going to go ahead and say certain. Given if you are watching this at home, this is going to be a little bit different, but I'm assuming you're in class, you definitely had school today. You flip a standard quarter and it lands on heads. Hopefully your answer is equally likely to occur because there is a 50% chance it will be head and there is a 50% chance it will land on tails. Okay, so now some more questions. What are the chances that the temperature outside today will be 100 degrees? I'm going to say likely, okay, because it's the summer, it's going to be warm. Number 5, the temperature tomorrow will be more than 50 degrees. Again, I'm going to say very likely because it's summer and it's pretty hot. Notice I didn't say certain because I am not 100% sure it's going to be more than 50% degrees. It's likely, but not 100%, so be careful. So let's go over some vocabulary real quick. An event is basically what we call an experiment. And if you're wondering what an experiment is an activity in which results are observed. So here, some experiments might be flipping a coin, or rolling a number cube. An outcome is one of the possible results from the event. Okay, and the sample space is the set of all possible outcomes of an experiment. So, for example, the sample space for flipping a coin, what are all the possible outcomes? Well, you could flip a head or you can flip a tail. Now, same thing with rolling a number cube. What is the sample space? Again, we're looking for all the possible outcomes. You can roll a 1, you can roll a 2, you can roll a 3, 4, 5, or 6. So notice sample space is basically all the possible outcomes. Okay, so now the scale returns. We're going to go ahead and describe where each event would be located on this scale. So, what is the chance of rolling a number bigger than 1 on the number cube? I'm going to say likely. Why? Because the sample space is, there's 1, 2, 3, 4, 5. The ones that meet this requirement are 2, 3, 4, 5, and 6. That is 5 out of the 6. So I'm going to go ahead and say that it's likely. Okay, if you did it mathematically, you would find that it's a 5 out of 6 chance. And if you convert that into a percentage, it would be 83.3%. So definitely likely. Real quick, this capital P is basically, you would read it as the probability of getting a number greater than 1. That's what it is. Number 7, flipping the coin and having it land on heads. So if we look at the sample space for flipping a coin, we know there's heads and there's tails. So it's asking us, what are the chances it's going to land on heads? Well, it's a 1 out of 2 chance, so that's 50%. So I'm going to go ahead and say it's equally likely to occur or not occur. And number 8, rolling a 7 on the number cube. Well, if you look at the sample space, the only outcomes are 1, 2, 3, 4, 5, and 6. So the chance of me rolling a 7 is impossible. It's 0 out of 6, which is 0%. So I'm going to say it is impossible. Number 9, it says, in this experiment, you spin the spinner on the left. List the sample space for this event. First, let's talk about what is this experiment? Well, this experiment is spinning the spinner. And then to answer the question, what is the sample space, I'm going to say you could possibly spin on orange or you can possibly spin on green. So my sample space is green or orange. Now, which color are you more likely to land on? Common sense tells me, since looking at this image, I'm going to say orange. But why? Well, again, common sense tells me there is more orange, the area is more orange than it is green. That's why it's more likely for us to spin on orange than it is on green. Now, how could you change the spinner to make it equally likely to land on either color? Well, in order for that to happen, we're going to have to change the coloring of the spinner. We would want to make it half orange and half green. So if I shade this back into green instead of orange, if this was perfectly half, then I can go ahead and say that now it is equally likely to spin on either orange or green. Now it's your turn. I want you to go ahead and pause the video and do a quick sketch of creating a spinner that satisfies the following. Number 1, I want you to make sure it's more likely to land on yellow than green or blue. But I also want you to make it equally likely to land on green or blue. So if you don't have any color pencils or crayons, simply label the area. For example, this is not correct, but I can just divide this area and call this one's going to be green. So again, if you don't have color pencils, just simply label it. Okay, so hopefully you don't have to have exactly like mine, but I would first shade a yellow area. I'm going to shade half of it. Okay, pretend it was exactly half. Not really good at this. And then because we want it to be equally likely to land on green or blue, I want to make sure those are equal in area. Okay, so imagine this is exactly half of this semicircle. So this part is green and this part is blue. Now real quick, is this the only answer? Absolutely not. There are various answers that would work. Okay, this is what came to my mind first. Now, real quick, to prove to you that there's more than one answer, you could have made all of this yellow and simply divide what's left into equal parts. So you can divide this equally to call this green, and then call the other section blue. Okay, and it's a quick sketch, so it's not precise, but you get the idea, hopefully. So future knowledge. Probability describes the likelihood that an event will occur. Okay, there's something called theoretical probability. It's when you take the number of desirable outcomes and divide it by the total number of outcomes. Theoretical probability is what should happen. Okay, under ideal circumstances, it's what we expect to happen. So in all previous problems, our guesses were based on theoretical probability. Okay, but experimental probability, which is the other type, is obtained by actually doing the experiments. So each experiment is called a trial. Experimental probability is still the number of desirable outcomes divided by the total number of outcomes. Now here, rolling a pair of number cubes, if you add the numbers that appear on top, okay, what is the sum that is most likely? And what is the sum that is least likely? I want you to think about that. Sometimes it might be hard to know what is more likely. So experimental probability can help us with that. So again, theoretical is what we expect to happen. So for example, like rolling a die, not rolling a die, flipping a coin, I expect it to be 50% chance of tails and 50% chance of heads. So in this case, it's going to be a good idea to actually do the experimental probability to kind of see what is it more likely to be rolled for a sum and what is the least likely sum. So here, I'm going to go ahead and give you a quick demo. So you can see here, these two dies have been rolled plenty of times, okay? This many times. So I can even show you if I roll it. I think that's the maximum, never mind. You're going to see, on average, a 2 was rolled about close to 3% of the time. A 3 was rolled about 6% of the time. 4 was rolled about 8%. 5 was rolled about 11%. 6 was rolled about 14%. 7 was rolled about 17%. 8 was rolled about 14%, and so on. So knowing this, let's take a look. Which one was more likely to be rolled? Well, simply take a look at the percentages. Which one happened more often? It was the 7. Now, what about which one's the least likely to happen? Well, that would be 2 as well as 12. So to go back to the keynote, to answer this question, let's take a list. Let's go ahead and list all the possible rolls to help us figure out the theoretical probability. Okay, so for a 2, the only opportunity is if you roll a 1 and a 1. Okay, what about a 3? Well, you can roll a 1 and a 2 or a 2 and a 1. We're assuming this is always the first die and this is the second die. Correction, this is the first dice, this is the second dice. Now, how can you roll a 4? Well, you can roll a 1 and a 3, 3 and a 1. Or a 2 and a 2. 5, you can roll a 1 and a 4, a 4 and a 1, a 2 and a 3, 3 and a 2. 6, a 1 and a 5, 5 and 1, 2 and 4, 4 and 2, 3 and 3. Notice I don't list 3 and 3 again because that's the same thing as 3 and 3, okay? So here, 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, 4 and 3. So I'm just going to go ahead and continue this. And you're going to see there is symmetry around this, okay? It's as likely to roll a 2 as it is to roll a 12. It is as likely to roll a 3 as it is to roll a 11, because there's 2 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So here, if you consider rolling a 3, it's 2 out of 36. Rolling 11 is a 2 out of 36 as well. A 10 is 3 out of 36. A 4 is 3 out of 36. So hopefully you see that pattern. But at the end of the day, we're answering the question, which one was the least likely? I'm going to say 2 and 12. But which one's the most likely? Definitely going to go with 7. And that's exactly what we saw in the experimental probability. So we will look at this in more detail soon. So we'll come back to this. So to answer the question, I'm going to say the sum of a 7 is the most likely. It was about 16.6% in the demo. Okay, and you saw in the chart it had the most combinations that made 7. The least likely was the 2 and the 12. If you looked in the actual experimental probability, that was about close to, I think, 3%. So it was pretty low. It was the lowest ones of all of them. So guess what? That is going to conclude the lesson for today. Thank you so much for tuning in. And as always, until next time, bye!